It's the last example of 4.6, the last example of the chapter. This is a cool one too. Always dangerous when a teacher says things like, this is a fun problem. And this one is, a fence is to be made to enclose a rectangular region of 108 square feet. All right, so we're going to put a fence around a rectangular region. We know we need it to be 108 square feet in the end. Along three sides, the materials will cost $6 per foot, and along the fourth side, materials will cost $18 per foot. Don't really know why. For some reason, it's cheaper along three of the sides. Maybe that other side, who knows? We need it to be a little bit more secure for whatever reason or another. Maybe there's a gate on that side. I don't know. But it's going to cost three times as much for the fourth side. We need to find the dimensions to minimize cost. Hey, this is pretty cool. Our other examples were all about maximizing. Now we're minimizing. Sure, you can certainly you want to minimize things sometimes to optimize. All right, let's check it out. For this one, kind of like that very first example we did, there's a similar feel. They're talking about a rectangular region. Go ahead and draw yourself that region. So I've got my rectangular region here, and I noted that this region I'm going to think of like the fourth side, the one that costs a bit more. I don't have to do that, but it just kind of makes it easy for me to remember how I thought of it. So I've labeled all four sides, right? X, X, Y, Y. We don't know. In the end, we need the dimensions here. We actually need the values of X and Y to answer the final question. All right. So that's all we got so far. We know a couple things. So the fence is going to enclose 108 square feet. And they don't say it explicitly, but that's an area, right? So we need that area to be 108 square feet. They also talk about cost. Okay, let's get to that in a minute. Let's start just with that area. Well, what's the area of my rectangle? Right. Well, x times y, right? Oh, looks like I'm going to reveal cost at the same time. Okay, area is x times y. How about the cost? The cost for the fencing all around. So if on the less expensive side, it's $6 per foot, remember that x and y represent feet. That's how long that side is, right? So if we take the number of feet and multiply by the dollars per foot, then that would be the cost of each side, right? So the cost of this side here is 6 times y. $6 per foot times y feet. The cost along the top is 6 times x and 6 times y. The cost down here, that's the more expensive one, 18 times x. Okay, now I'm going to reveal it all. There's my area. That's my constraint. I know that x times y is going to be 108. And for the cost, starting there, 6 times y, 6 times x, 6 times y, and the more expensive side, 18 times x. I'm going to go ahead and simplify this cost by combining x's and y's. 24x plus 12y. Okay, so I have my cost in terms of x and y, right? Of course, I want my cost to just be in terms of x. How am I going to do that? Well, I can go back over here, solve for y, substitute that in. And that won't be too bad. Y equals 108 over x. So when I plug that in, c equals 24x plus 12 times 108 over x. Simplify it a little bit. C equals 24x plus 12, 96 over x. And we have the function to represent the cost. Now I'm actually, yeah, we're good with that. Okay. Then of course the other question, once we have that function, well then what's the interval of x, right? What are the possible, what's the lowest and highest x value? What's that interval going to be? Okay, so this one, now this problem really differs from the other three. And it's nothing that you could have foreseen. It's just the way that it's gonna play out. So remember that constraint. Okay, often the constraint is the key to figuring out the largest and smallest x values. Okay, if x times y equals 108, what's the smallest that x could be, and what's the biggest that x could be? And now it gets a little bit weird. So I'm just going to show you how it comes out, and I'll just try and justify that. All we know is that x has to be positive. X has to be greater than 0. That's all we know. Clearly, x cannot equal 0, because 0 times anything wouldn't be 108. But x can be as small as we want up to 0. X could be 0.1, or 0.01, or 0.001, because there's a y value that we can multiply with to get us back to 108 for the total area. Right? Also, x, there's no biggest value of x, because we could make x huge. We can make x 1,000. There's a value of y that we can multiply with 1,000 to get 108. We could make x 1,000,000 or 1,000,000,000 or whatever. We would just have to in turn make y smaller and smaller and smaller to make that product work. So all we know is that x is positive. Certainly it can't be 0, and it can't be negative, because we're talking about a rectangular region and the number of feet. So we know that x is positive. That's it. So our interval is 0 to infinity. And I understand if people are like, wait a second, what? Like, there's no biggest value of x, there's no smallest. If you thought about that rectangular region, right, x, y, you could shrink, you could start to shrink y down, but as you shrink down y, all you got to do is make x bigger and bigger and bigger, and you can keep the area at 108. Or you could make x smaller and smaller and smaller. All you got to do is make y bigger and bigger and bigger and keep that area. Kind of a different way of looking at it. Now, luckily, we did have these sort of intervals back in 4.5, so we're going to follow that procedure. Okay, oh, looks like that page is out. Let's move along. Okay, so here we go. We want to minimize c equals 24x plus 1296 over x on that interval 0 to infinity. Now, because we're going to take a derivative, I'm going to rewrite that second term. Think of it like this. 24x plus 1296 x to the negative 1. Much easier to take a derivative this way than with the quotient rule. Okay, so if I go ahead and take the derivative now, boom, got it. 24 minus 1296 x to the negative 2 when I subtract 1. And I'm actually going to go ahead and rewrite that, go back to the fraction form. Like, oh my God. Why? Well, because I'm about to set it equal to 0. And it's much easier to work with the fraction form when solving these things. Also, I want to consider when the derivative does not exist, and much easier to think of it in the fractional sense for this one also. So what's about to happen? Okay. Oh, page sticking to my finger. Let me just show you what I've got here. Okay, there we go. That's the whole page. All right, no problem. Let's look at setting it equal to 0. So we can add that part over, multiply, divide by the 24. I'll advise you to check all of my work here. Take a square root, and I'm just going to go ahead and round that to 2 decimal places. It didn't say it in the problem. I'm not really sure what MathXL wants you to do, if they want you to keep the exact form or round. If this was a test, I definitely prefer the rounding because it's an application. We prefer rounded numbers in applications usually. At least I do. So we end up with 7.35 as a critical number after solving the derivative equal to 0. Also, when you consider the D and E, there is one because you might divide by 0, right, if x is 0. So at first this seems like another critical. Oh, but wait, the interval was 0 to infinity, and that is not in the interval 0 itself, so we can just forget this critical number. We just get the one critical, and you may have noticed that theme in all of these problems. We only have the one critical number. That's very common in these optimization problems as well. Okay, so this is interesting now. We only have the one critical number, and our endpoints are 0 and infinity. So usually, right, in the other problems, we took our one critical, plugged it back into the original C. Same with the endpoints. Well, we can do that for 7.35, but 0 and infinity, and we shouldn't even actually include 0, let alone infinity. What do we do with that? If you remember back in 4.5, what you do with these kind of intervals, you do plug this in to the original C. So that's what I've done next. Okay, and I just went ahead and showed you what I got. I got 352.73 when I put it into the original cost function. But at this point, we don't know if that's a max or a min. Right? We're supposed to minimize. We need to show that this really is an absolute minimum. So what we're going to do, all right, is that a max or a min? We are going to check that x value in the second derivative. That's double prime, the second derivative of c. We do this because we're going to check the concavity. So let's take a look. Okay, so there was the first derivative from a moment ago. Let's take a second derivative. Okay, that -2 multiplies down, drops to a -3. It's 2592 x to the -3. So we're going to put 7.35. Oh, and I went ahead and converted to that way, I guess. All right, sure. So either way, so I plugged in 7.35 into there, and well, I got 6.53. The number is not important. It's the fact that it's positive, because the second derivative test tells us that if we are both concave up and the first derivative equals 0, which we showed a moment back, you're concave up and you know you're at the location where the first derivative is 0, there's a horizontal tangent line that must have occurred at a minimum, and that's what we wanted. We wanted to minimize the cost, and we've done it. X equals 7.35 will minimize the cost. Hooray. And we can now answer the question. What was the question? Find the dimensions to minimize cost. So we know the x value. We got to go back and we got to find the y value that for that rectangular region. So we'll plug the 7.35 in, and we'll realize that y, in that first rectangle, was it y, x, and this was the more expensive side down here, x. The dimensions we just think of as x by y. So we've got the x value, we've got the y value, the dimensions of our region, 7.35 feet by 14.69 feet, which tells you that my drawing is not quite accurate. The shorter side is actually the x, and the longer sides are the y. Makes sense that you would put the shorter side on the more expensive materials if you had the choice. So our x, our y, this number of feet by this number of feet, that's how you represent dimensions. That is it for this section. See you guys in the live session.